All right, so we'll get started. We are in a bit of a time crunch, but we can definitely get through this. So, what are neural networks? You guys have probably heard of like neural networks. I don't know. A lot of times, they are pretty much used in every piece of software that you use. That is, I don't know, depending on like what sort of use applications are you have. So, some well-known examples are ChatGPT. Essentially, what neural networks do is that they are a simple way to create a mapping from your input to a desired output. So what this essentially means is that, I don't know, if you have some input data, for example, if you have visual data, what your brain essentially does is it creates a mapping from visual data to, for example, say things like faces. Your brain takes in visual data and I can identify her face or I can identify his face based on the visual information that I get. So in my mind, my brain is essentially creating a mapping. And what neural networks do is they try to like sort of simulate a similar kind of mapping. And what this can basically do is we can get a lot of useful things out of it. So for example, full self-drive, I don't know if you guys know this, but Tesla is at least attempting to do this. It has input of visual data and it outputs driving instructions. And you can see that's pretty cool. They can basically simulate human driving with the help of this neural network model. So how neural networks look? So this is a typical structure of a neural network. You have an input layer, you have hidden layers, and you have output layers. All of these things essentially have a bunch of parameters. So this small neuron right here will have some parameters. This neuron will have some parameters. And essentially, this network is made up of all of these different parameters. And what a neural network's job is essentially to optimize all of these parameters so that your input from here, when it gets to here, looks like your desired output. So, for example, essentially, imagine that your task is given a sort of images. You want to predict whether the image is a cat or dog or I don't know some other animal. You want this network to have parameters essentially such that when your input image goes in from here, it should always predict a dog when the image is a dog or a cat when the image is a cat, and so on. So the whole challenge of neural networks is essentially to optimize all of these parameters. That's it. That's all you need to do. So to get started with some code, essentially what we're going to be using is a library called PyTorch. And PyTorch has these things called tensors. Have you guys heard of like NumPy arrays or like arrays in general? Yeah. So tensors are basically similar to like arrays. The only difference is that you can do something interesting called, you can call dot backward on it. So what does dot backward do? So look at this simple example of tensors. Y is equal to x squared. That's like a relationship between two tensors, y and x. Now, what you can do is essentially, if you want to calculate the gradient that y has with respect to x, that means if you want to calculate dy by dx, you get something like 2x, right? That's what you know from basic calculus. And when x is equal to 3, you get the gradient as 6 because you just plug in 3 here and you get 6. So why does this matter? So essentially, as you remember, we were trying to optimize the neural network that we have, and we want to optimize the parameters. So the way you want to optimize it is essentially you'll have something called a loss function. A loss function basically tells you how far your network's predicted output is from the true output. For example, if your network is attempting to predict for a dog and it predicts the output as a cat, that's a pretty big mistake. That means your loss function will essentially be really high. What you aim to do is essentially you want to minimize this loss function. You want to reduce the distance between the true output and your predicted output. Now, if you guys remember from calculus, minimization requires us to take gradients. If I want to minimize this, I'll like set the gradient equal to 0 and then I'll solve for x. Now, and if you remember, y is equal to x squared as a minimum value of 0. So essentially, when we set this value equal to 0, we get x is equal to 0. So what you want to do is essentially you want to do this for all of the parameters in your network. You will essentially take a derivative of the loss with respect to each individual parameter and then use that derivative to minimize the loss function. So we'll get to some code examples first. So as you can see here, wait, I'll just like share the notebook in case you guys want to follow along. Most of these things will be public, but just for the sake of it, I'll like share it. Yeah. So as you can see here, the syntax for creating a tensor or an array for which you can get a gradient. That's what a tensor is. Essentially, just torch your tensor, the value that you have here. And this is very important. You have to set required grad equal to true. Otherwise, you cannot get any gradients for this tensor. Now, what we do is we essentially let y also be a tensor that's x squared. And when you call y dot backward, essentially what this does is it finds all the variables that y is dependent on. In this case, it's just one, that's x, and it sets its gradient. So what you can see here is when you print the gradient, that's x grad, you should essentially get something like 6. Why? Because x squared has a gradient of 2x, and when you put in 3, you get a value of 6. Now, the cool thing about tensors is essentially you can do this for multidimensional output. This is the x is composed of like 2 3-dimensional vectors. You can again, I don't know, plot something like y is equal to x sum. So that's again a relationship between y and x. And you can call backward and you get this sort of confusing gradient. But basically what you want to know is it works. Now, a gradient of indirect connections. So remember that I told you that essentially all of these are parameters and you'll have some output that comes in here. So the issue with this is that if the output is here, you can calculate the gradient of this parameter with respect to the output. That's pretty easy. That was like the y is equal to x squared sort of thing. They are pretty directly connected. But what about this parameter or this parameter? They are not directly connected to the output, as you can see. So it's really hard to figure out how this parameter influences the output in any way because of this weird indirect connection. So there's a simple way to sort of address that. And that's essentially to use chain derivatives, as they're called. So imagine y is equal to x squared and z is equal to 3y. As you can see, there's an indirect connection between z and x. You can't directly calculate the derivative of z with respect to x. So what you can do it, you can solve it using a trick. So imagine that you want to calculate dz by dx. What you do is you calculate dz by dy and you multiply it by dy by dx. As you can see, both of these are the same things, but z has a direct connection to y and y has a direct connection to x. So we know both of these quantities and we can calculate both of these quantities. And essentially that's how you would calculate dz by dx. Now that you know this, essentially, for this network, if I want to calculate the influence that the output, say influence that this has on the output, I'll calculate the output derivative with respect to this, multiplied by this parameter's derivative with respect to this, and with this, and so on. And that's how I'll get basically the influence of this parameter on the output. So this is again like a simple code example that does the same thing. As you can see, if you do a bunch of calculus, the derivative of z with respect to y is just 3, and this is 2x. So when you multiply both of those together, you get 6x. And when you put in a value of x is equal to 3, your basically gradient should be 18. And that's what basically TensorFlow, sorry, the PyTorch does for you. Once you call it backward, you get all of these gradients set. Now, okay, this is a simple example of why I was talking about basically calculating gradients. You'll have your loss function that sort of looks like this, right? Imagine the y-axis is your loss. The loss essentially, again, to repeat myself, is the distance from your predicted output to the true output. A higher loss would mean that your model is bad or good. Does anyone know? Bad? Yeah, exactly. So what do you want to do? You have to bring this loss all the way down to its minimum. The less loss that you have, the better model that you basically have. Now, imagine that you have one parameter, that's p, okay? I don't know if you guys remember from calculus, but when you take a derivative, it essentially gives you the direction of highest ascent. That means when you calculate the derivative of the loss with respect to one parameter, it'll give you the direction in which loss rises the fastest. So as you can see, it goes up. We don't want that. So what will we do? We negate this. When you negate this value, what you get is this arrow flips down like this, and you get the direction of steepest descent. That means that essentially you'll get the direction in which a parameter needs to move in order to have the least loss possible. Now, what you'll do to basically adjust this, essentially you'll calculate this and you'll add it to p. Now, what happens when you add the small like derivative to p? P will move from here to here. And as you can see, as you keep doing this, P will keep on moving in this direction until it reaches here, and then it will stop. And that's exactly what we want. We want the P for which the loss is maximum. Now, as you can see, I did this for one parameter, but we want to do this for all parameters in the neural network. When you keep doing this for all parameters in the neural network, your loss overall will keep on decreasing. And that's why gradients are important here. Just a quick note, you can definitely, like, technically speaking, if you want to code like a neural network based on some random data you pulled from Kaggle or some other site, you don't need to know this. But the issue is that no one's ever going to test you on like just solving a machine learning problem for a random data set. They're going to test you on whether you know all of this like under the hood stuff. Because essentially the way I thought of all of this material to teach is I went to ChatGPT and I asked it to like explain a neural network to me. And the reason why I did that is because if all of this information was as easily explainable by ChatGPT, then you wouldn't really need me here to explain this to you. So if you like input a random data set to ChatGPT and tell it to like construct a neural network, it probably can, but that's for a very basic case. If you ask it to calculate a neural network for something like a complex image data set that has differing values, it kind of struggles, and it kind of struggles even more for like more complex problems. Here's your hand. Yeah.
So like with loss functions, do we need to constantly recalibrate and reconstruct our function every time we add more parameters, or is it like with our model, once we figure out a good function, it will work?
So if you add more parameters, then yeah, you potentially need to recalibrate your loss function. If you have the same parameters, then all you need to do, like the loss function will be the same, but the loss value will be different each time you update the parameters. Now, if you add more parameters and your neural network changes, potentially you might have to change the loss function itself. And so normally when we are like updating a neural network, we don't add more parameters. We decide on a set number of parameters and then try and update them. But if you add more parameters, then you'll need a new loss function. Does that answer it? Yeah. So you get the gist of why essentially we need derivatives. Now we'll actually talk about each individual neuron. So a neuron, so neurons lives in forward passes. So as you can see in this image right here, these are individual neurons. These are layers. And as you can see, each layer is made up by a set number of neurons. Now, if you want to, I've been talking about like moving input through this neural network all the way to like get some output. But if you want to actually know how that happens, what you need to do is imagine some input here. So I'll explain how this works. Each neuron here just outputs one number. So essentially you'll have one number from neuron 1, neuron 2, neuron 3, neuron 4, neuron 5. So you'll have a set of 5 numbers. And the way you get the output of one layer is essentially you create like a vector or a set of elements, if you can call it that, and you basically join all of them. So you'll have something like element 1, 2, 3, 4, 5 in like one vector, and that's essentially your output for this layer. And what you need to realize is that each layer only depends on the output from the previous layer. So if you can imagine that if your input is a bunch of numbers, you arrange them one below the other. So if you have a four-dimensional input or an input with 4 different numbers in it, you'll arrange it as number 1, number 2, number 3, number 4. And all this will do is this layer will essentially take that input, process it at one neuron, at the second neuron, third neuron, fourth neuron. Once your input is processed at the first neuron, you should get a real number here. The same thing will happen at the second neuron, you'll get a real number here. The same thing will happen at the third neuron, you'll get a real number here. And at the end of it, once all these all of these neurons have processed the input, you'll have a set of 4 numbers right here. And essentially you like compress them and you get a set of 4 elements, and that'll be a new input for the next layer. That's how you do it. So if you want to know how the individual neuron processes one input, look at this diagram. So imagine that this is your input at one particular neuron. In this case, we are assuming that it's a 3-dimensional input or input with 3 different numbers. You have x1, x2, x3. Each neuron has something called weights, which are the same parameters that I was talking about earlier. These weights, what you do is essentially you take the first number. If, for example, a neuron has 3 weights, you take the first number, you multiply it by the first weight. You take the second number, you multiply it by the second weight. You take the third number, you multiply it by the third weight. You add all of them together, and as you can see, you'll get one number, right? And that's essentially the output of the neuron. There's something called an activation function here that I'll talk about later. But I have like a small example for you guys to see. So imagine that this is your input right here. Any neuron that you have in the layer preceding, in front of this input will essentially have the same number of weights as you have inputs. So this neuron can never have 5 weights, or it can never have 6 weights. It needs to have 3 weights. This neuron, as you can see, because after we process all of these numbers through these 2 neurons, we get a 2-dimensional output. This neuron can only have 2 weights. So I'll now explain how this works. So you can see here that we have 1, 1, 1. The output at this neuron will essentially be to multiply 1 by 2, 1 by 3, 1 by 4, and you add all of them together. So when you add all of them together, you get a number called 9. This is the output of this neuron, that's 9. Once you do the same thing for this, you get 15. Once you multiply these numbers together, you get 90. And that's how information moves through a neural network. So do you guys get an idea of how inputs are transferred into outputs through neural networks? Yeah? Does anyone have any questions? Yeah, go on.
Why does layer 1 have 2 different things instead of 3?
Like, why does it have 2 neurons?
Yeah.
That's just a choice I made. So that's the customizability that you guys have in neural networks. It could be 100 neurons that I've put here. It's up to us to experiment and figure out what's the optimal number of neurons to have here. 2 here is just for an example.
And then like parameters and neurons are parameters, just another word for a neuron in an actual machine learning.
So they're sort of different. The thing is that each neuron, as you can see here, it has 3 parameters here. It's not just 1 parameter, right? So each neuron in and itself has some component parameters. But in a sense, yeah, a neuron can be considered like a high level parameter, if you can say it. But yeah.
What is the 5 and 3?
That's again, these are random weights that I've just set here. You have to imagine that these are weights that, let's say, after optimization, you get all of these different numbers at these positions. 5, 3 can either be some random number that I found through training this neural network, or it can be the first initial value that I'm using to train this neural network. These are just examples to show you how input moves from one direction to the other. So this is just like some sample computation that I've done. It shows you how numbers are multiplied and how you get an output. So now that you remember the earlier example that I showed you, in it, each weight was like in a separate component, right? Like I had a weight for neuron 1 here, a neuron, weight for neuron 2 here, and that's how I did it. The thing is that if you keep on multiplying your input with this neuron individually, it takes a lot of time. So what you can do is essentially you can take all of these different weights and sandwich them together into this one big, it's called a matrix, but I mean, it's fine if you don't know that. It's called a matrix. So you sandwich all of these different weights into one block. And what this allows us to do is essentially this input can be multiplied with this block directly. And as you can see, there are 4 different neurons here. That means the output of this layer will be how many, like, what will be the size of the output of this layer? Can anyone tell me? If you have 4 neurons right here, it should be 4 dimensional, right? Or it should have like 4 different elements. So once you multiply this input, you'll get a element here, an element here, an element here, and an element here, and you'll get 4-dimensional inputs. So essentially what you want to do is that each layer, you'll have this block of values that represent the layer itself. That means you have a block of values of all the weights of each individual neuron right here. So for example, if you have 4 different layers, you have 4 different blocks with all of these different weights. So this is a simple neural network example that I've made. What you can see here is our first neuron, if you remember from the example, it's 2, 3, 4. Those are the weights in it. The second neuron has weights 4, 5, 6 in it. The input is 1, 1, 1. The dot T there basically says that if you have like your inputs as 1, 1, 1, we want to like make them into a straight line. I don't know how if you guys have taken linear algebra, but in that term, it's basically it needs to be a column vector. All you guys need to know is essentially you do this dot T just so that you can multiply 2 things together. That's all. Like it's not really complex. For neurons 2, 1, that's the second the neuron in the second layer that we had. We have 5, 3. So what you can do is essentially you can sandwich both of these neurons into one weight layer. So you can see weight layer has a tensor that is the weight of the first neuron combined with the weight of the second neuron. you just have these two lists that basically show neuron weights, and you just like combine them using this comma. Now what you want to do is essentially ignore this line, go to the layer one output weights, you matrix multiply. That's the basically that's a big function that you guys need to like learn. It's called torch.matrix multiply. And as you remember, we basically multiplied the values of our input with the weights at a neuron. Here, as you can see, I've multiplied them individually. I multiply neuron one's weight with the input and neuron two's weights with the input. And here I multiply the weights directly with the input. As you can see, this is much more easier. If you have like, I don't know, a million different neurons in one layer, you will have to keep writing this for like 1 million times, which is impractical. So you would rather combine all of them into one weight block and essentially multiply the weight block with the input. Then what you do for the output is do the same thing. You'll multiply the neuron two weights with whatever output you got from layer one. And as you can see here, layer one output weight was 915, similar to the example that we calculated. And your final output was 90. These two examples were just to show that you can do it in two separate ways. Ideally, you'd only want to do it in this weights manner. Any questions? Okay, so the activation functions. So I don't know if you guys remember, but like in that example I showed for calculating the output at a neuron, after you multiply all of those things together and add them, you also apply something called a activation function. Now, I don't know if you guys have taken biology, but essentially our biological neurons have like a threshold after which they activate. And what people who actually wrote the first paper for artificial neurons try to do is essentially replicate that activation here. Now, why, like, I know in a biological sense, it like the question that I thought of was, I mean, I get that biological neurons have a threshold, but why do we need that here? Like, it's fine if you don't make it as biologically accurate as possible. But the challenge that you essentially get is if you don't have these activation functions, you can only solve problems which are linear in nature. So I'll explain what linear problems are. Okay. I don't know if you guys have heard of linear regression, but essentially linear regression is the task of fitting a line to like to some data. So as you can see here, if you want to classify two different points, imagine that these are dogs and these are cats. If you want to classify them, you can simply draw a line and it does the job, right? This is called a linear problem because you can draw a line to basically solve this problem. A non-linear problem is one which can't be solved using a line. There is no line you can draw in this example that will be able to like classify these points and these points separately. It's not possible. And the thing is that in nature, you have very few linear problems as compared to non-linear problems. Identifying a face based on visual data is a really complex problem that is probably not linear in nature. Our brains probably calculate a variety of different non-linear solutions to basically get someone's face. So what essentially that you need to know is what makes neural networks so special is that they are able to solve non-linear problems. They are able to solve very complex problems. And the only reason they can solve this is due to these activation functions. So as you can see here, this is a solution that is given to us using a neural network. You have this weird problem that again, as you can see, there is no line I can draw to basically like replicate this curve, right? Essentially, I can draw this line, but it won't cover this part. I can draw this line, but it won't cover this part. So what we do in neural networks is we use activation functions to basically create small lines to replicate stuff. I've created a bunch of different lines to replicate this curve. And as you can see, it sort of fits the data quite well. You can see how neural networks, essentially using activation functions, can slightly fit nonlinear data much better. Now, this is activation function called ReLU. So what you do is, I'll just show you different activation functions. This is the ReLU function. This is very widely used in neural networks. This function is applied after each neuron's output. Now, what this means is essentially, if, as you can see, it's zero up until like the zero value, and then it's positive. The ReLU function is simply take your value. If it's negative, equate it to zero. If it's positive, keep it as it is. So if for example, I want to show you like an, I don't know if I've done this, but okay. If I have a value of, I don't know, if I have like, let's say an output at a neuron that's -1, 1, 1, Does anyone know what will happen if after I apply this ReLU function to it? Yeah, but what will the exact output be? So your input is -1, 1, 1. Yeah, correct, exactly. So that's what's basically happening. What these functions essentially do is it breaks your prediction into these weird lines. It just breaks your prediction into these weird lines. And as you can see, essentially, these weird lines being broken is the only reason why you can use lines to fit this in the first place. That's why these activation functions are essentially what make neural networks worth it. So there's another activation function here that's called a softmax. Softmax is really important. As you can see, it's 0 up until like this value, and it's really, really high there. So essentially, if you have a value that's really high, that's the only case when it's going to be non-zero. And if it's really low or even negative, you're just basically going to have it as 0. Um, yeah. So softmax for classification tasks. Essentially, imagine that I think I talked about like a dog and cat problem earlier. If you want to like predict for if a certain image is a dog, a cat, or let's say you have 5 different animals that you want to predict for. At the end of your neural network, you'll have a 5-dimensional output, right? You want basically your output size to be the number of classes that you want to predict for. So at the end of your output, you'll essentially have this, a 5-dimensional vector. Now the thing is, you can't really tell if it's a dog, a cat, a horse, a monkey, or let's say a hippo using this. You have 5 random numbers. Like, how are you supposed to make a prediction based on that? What you do is you apply a softmax on it. And what a softmax does is essentially it converts all of these numbers into a probability distribution. Now you can see that the fact that it's class 3, let's call this like the horse class. Let's say the horse class is class 3. It has a 99% probability that your image is a horse. It has a really low probability it's a dog. It has a really low probability it's a cat. And it has really low probabilities of these other 2 animals. When you apply softmax to any given input in your neural network, it converts it into a set of probabilities. And essentially, this will help you. I don't know, if you want to predict based off of this, you take the maximum, which is the third value, and you get class 3. You compare the actual output to your output, and as you can see, this predicts for class 3, the true output was class 3. And that means your model is doing pretty well. That's how you use softmax. Now, we are going to basically be looking at a set of problems that are called they're called multivariate classification. What this means is essentially the same problem as I told before. If you have a bunch of input images, if you have a bunch of input data, and you want to predict for different classes, for example, if you want to predict if your input data signals that your input is a dog, a cat, a horse, or many different classes, that's called a multivariate classification problem. And remember the loss function that I was talking about earlier? So essentially, for multivariate classification, this is the loss function that you essentially have. Now, why is this the case? Let's take an example where you just have 2 classes, 0 and 1. That's how we like classify them. If you're predicting correctly, what this will happen is essentially, imagine that this is the true output and this is the predicted output. If you have 0 right here, as you can see, it won't matter whatever this is. So if you have 0 predicted correctly, and if you have 1 as the true output, you will essentially have 0. This means that your loss is like really low, and that means that's exactly what you want to have. But if you're predicting incorrectly, if for example your prediction is 1 and the true output was 0, you can see that this log of 0 tends to around infinity. That means your loss will be like unimaginably high. And that'll mean that you need to basically alter your loss. Now, in real terms, we normally don't use zeros or ones. We use values that are close to 0 or 1. As you can see, if I put in a 0 here, it basically equates to infinity, and our computers can't handle that. So what we do is we essentially truncate it to be something like 0.0001. So I know that this is kind of complex, but all you need to know is this is the loss function that you'll use to basically check how close your output is to the true output. How close your predicted output is to the true output. And now, if you remember going back to like what we started with, you'll basically want to use your loss function to update all of the weights in your neural network. You'll calculate a loss, then you'll take a derivative with respect to each weight in your neural network, and you'll shift it towards a direction of minimum loss. This loss function can differ based on the problem that you might have. There's something called a numeric problem. Sorry, there's something called a numeric classification problem in which, for example, you want to predict like the stock price. This won't really be a good loss function for that. Because I mean, this doesn't really make sense. Something like figuring out the absolute distance between your predicted stock price and the true stock price is a good indicator. For example, if you put in values of 0 and 256 here, it won't really make any sense. But if you put them through, like, let's say, an absolute difference loss function, which is 0 minus 256, then you get a good idea of how far you are from your true desired output. So just to like make it clear, the loss function update weights according to like minimizing this loss function. And that's essentially all you have to do in this neural network. So the learning rate is something that's really important. So remember when I told you that we basically calculate a gradient at this point and we move your parameter in this direction? To do that, you essentially have to multiply your direction by some small magnitude. I don't know if you guys remember this from, again, this is calculus 3, so it's kind of complex. But when you calculate a direction, you also want to calculate the amount you want to move in that direction. And if you look at this carefully, you'll have something like this, right? The direction of maximum descent. If you move in this direction by too much, what will happen? You move in this direction by too much and you get somewhere like here. And then you keep doing that. And if you move in this direction again by a big amount, you'll get to here. And as you can see, that's not desirable because it's really hard to reach this minimum. But if you move in really, really small steps in that direction, you won't even get to this minimum. You'll be stuck right here. After like a million steps, if you're like moving very, very slowly and you keep going down, and then at the last step of your training program, essentially you reach here, that's not a good like loss function with respect to your parameter. So what you want is essentially you want this rate of descending this loss function, or the rate by which you multiply your direction to move down this loss function, to be good. Now, the way in which you move down this function is essentially you take your original parameter, which let's say is valued right here, and you subtract the gradient multiplied by learning rate. That means you move it down by the magnitude of the learning rate in this gradient direction. So as you can see, if you keep doing this, your parameter essentially keep moving in this direction until it reaches here. This is the updating step. This is what you'll do for each parameter or each weight in your neural network. Now, when you keep going down, this is essentially a sample neural network that I've implemented. Take a good look at this. I've like linked the Python notebook, sorry, the Colab notebook in the Discord. You can use this example to essentially code your own new neural network right down here. So I'll like explain the example right now. Essentially, imagine that you have a data set. You have a bunch of different inputs. What you want to do is essentially, you want to calculate your weight layer. Now your weight layer will depend on the input that you have. This input right here has 3 dimensions. So as you can see, having a weight layer that's 2 by 3 means that each neuron will have 3 weights, and there are 2 neurons in this. We are, like the previous example, we are combining a list of size 3, which represents the weights, and we're combining 2 different lists for 2 different neurons. So this weight layer will essentially mean that you have 2 neurons of 3 weights. The layer 2 that you have is your final output. This means that you'll essentially have 1 neuron with weights, with 2 weights. This sort of resembles the earlier example that we talked about. I just want to like code it and like Python so you guys can do it yourself. Now the training part. Epochs is the number of steps that you want to train your neural network for. This will highly depend on how complex your problem is. If your problem is really complex, your epochs will be really high. And essentially, for each input in your data set, that means for each data point in your data set, you will first put this through your neural network. So you'll multiply your data point by the first weight layer, then you'll apply your activation function, which we didn't talk about earlier. But essentially, you'll apply an activation function here. Then you'll apply the second weight layer on your new layer's input. And at the end of it, you'll basically have an output. This is a sample loss for this kind of problem. You need to look at this, but essentially, this means that we have calculated the loss based on the output layer. And then you call dot backwards on this. What happens when you call dot backward on this is that the gradients that we are talking about for so long, the gradients of the weights with respect to the loss function, get calculated for each different weight in this weight layer. Now comes the updating step. What you do is essentially for each weight in this weight layer, you multiply this learning rate times the gradient. And you do this for the second layer as well. And after you do this, you want to obviously set the gradients equal to 0, because with a new loss calculation, you'll have different gradients. So this is the important updating step. Take all of your weights, subtract the learning rate times the gradient to move them in the direction of minimum loss, and do this for all weights in your neural network. And as you can see, this is for one input. You keep doing this for all inputs in your data set. And then you'll basically have weights that are really minimum compared to weights that are really optimized compared to like a minimized loss. That's what you basically want here. So after running this, as you can see, the loss that I got in the first run was basically 0.005. The second one was 0.004. Third one was 0.002. As you can see, after each run, the loss that I'm getting is being lowered and lowered because the weights are being updated in the correct manner. So the final and most important piece is called stochastic gradient descent. The function that I showed you that sort of looked like a U for the loss function, that's not really how loss functions look. This is a more accurate description of loss functions. Now, if you start right here, the point you want to get to is here, right? This is the minimum loss that you can get in this particular scenario. But the weird thing is that you can also see that there are these weird like holes in which if you descend down it, the minimum loss will also keep on updating accordingly. So for example, if you take this path, then you'll get to here. And essentially after that, the gradients of all weights with respect to your loss will be 0. Because imagine that at the point that's at the bottom of this like weird graph, these gradients will all be 0. But you know that this isn't the smallest loss that you can get. The smallest loss that you can get is over here. So something like this is called a local minima, which means that it's a point at which you can get a minimum loss with respect to gradients, but it's not the true minimum loss. What you want to get is the true minimum loss, which is called a global minima. Now, the issue that happened with our earlier example is that we were calculating the loss over all data points in the data set. So as you can see here, for each epoch or training run, for each point in the data set, we're calculating the loss and updating parameters. What this does is it can lead to like a loss function going into a local minima, and that's not what we want. So on a high level, you want to avoid calculating the loss for each point in the data set every time. What you'd rather do is something called stochastic gradient descent. What this essentially means is that you take a derivative of many different inputs that are randomly sampled from the data set. Essentially, what this means is that you have a data set of 1,000 examples. You'll randomly pick 20 out of them and then calculate the loss function and update it. Then you'll pick another 20 random examples and you'll update it and move the loss function down again. And what happens is that essentially, instead of moving uniformly like this, it will move in a weird zigzag manner. And this will avoid getting into one of these local minimas. So instead, you'll move down this path, probably to the global minima. So what you need to remember here is essentially when you're training, you want to calculate the loss with respect to a small subset of your data set each time. And that you keep on repeating that until you get a satisfactory loss. So this is like the final important part of the workshop. You can code this yourself. I don't know if you guys are in the meeting. Okay, what's up? So I don't know if you guys are in the I don't know if you guys are in the collab, but this is like an example for you guys to code yourself. I don't know if you have time for that. So what I'll do is I'll just help you code it. So for example, MNIST images are 28 by 28. Can anyone tell me what the input size will be? Remember that our original input size for the example that we used was 3. So can anyone tell me what the input size for this will be based on the fact that images are 28 by 28? Can anyone guess? Yeah.
Like seven, sorry.
28 squared.
Yeah, 28 squared.
Yeah, exactly. Yeah, so that's I think 784. If it's not, then we'll find out. The hidden size is something that's up to you. So remember you asked a question that said, how do I decide the number of neurons that are in the one particular network? That's sort of completely up to you for these hidden layers. You can vary it to get better results, Normally, something that I've seen from papers is essentially you want to choose your input size divided by around a factor of, divided by a power of 2, and you have to make it close to a power of 2. I know that's confusing to think of, but imagine that for this example, we divided by around 8, and we have to find the closest power of 2 that's close to, like, I don't know, something like 100. So I guess like 128 is a good size for our hidden layer to be. Now the output size. The fashion MNIST dataset has like 10 different classes. Just to like inform you, fashion MNIST is a dataset that has many different images of clothing items or purses or boots. So as you're talking about the animal example, instead of having animals here, we're having different pieces of clothing or purses here. And fashion MNIST has 10 different classes that you can output to. So can anyone tell me what the output size will be here? 10, yeah. Okay, now comes the, I guess, sort of challenging part, figuring out the first weight layer. So can you even figure out based on the example that I gave earlier, what the exact code for this will be? You can write the basic code. It's autocomplete, but yeah, can you even guess what this is? Okay, I guess like it autocomplete or whatever. Yeah.
You can turn it off.
Yeah, how?
Go to settings on the top right,
Mm-hmm.
and then it's AI assist, and then you can just turn it off.
Okay. So I guess like this gives you a hint for like how the second one should be. It essentially, also this is not correct. Can anyone tell me what's wrong here?
It says random n.
So this is still correct because you want to like you want some random values for your weight vector, right? It needs to have some values to start with, and then you'll move down in the correct direction. This needs to have something else as a parameter here. As you remember from our example, if you want to calculate gradients, what do we need here?
Resonance of gradient is true.
Correct. Yeah. Okay, and can anyone guess what this will be? Yeah, can anyone guess what the dimensions of this will be?
Would it be input size and output?
So look at it this way, right? Your weight layer for the first thing will essentially have input size multiplied by hidden size. After you get this hidden size is the number of neurons that you have in that layer. Remember, if you have like 5 neurons, what will be the size of the output at that layer? It will be 5, right? So this will essentially have a size of hidden input, so hidden size as your input, and you'll have your output size as your output. So you can just put that in. Oh, my bad. Yeah. We have basically, I don't know, just for the sake of it, we have had like 10 training loops because we have like, I don't know, we have like less time, and for some reason my computer doesn't like run these loops pretty quickly. So we'll just do 10. Now, this is the sort of important part. Remember that the images from your data set might not match the 728 dimension, 784 dimension. You have to first see what the dimensionality of your images is. In this case, it's something like 32 by 1 by 28 by 28. So a thing that I sort of like skip forward was essentially you get the data from these weird functions. You don't need to remember this. You can literally copy this from ChatGPT to get data from a data set. What you need to figure out is the actual training loop. So what this training loader essentially does is it chooses a batch size of 32 and it gets all of your data into those batch sizes. So remember when we were discussing stochastic gradient descent, we were like, we should pick a subset of the data in order to avoid local minimas. This subset right here is of size 32. So essentially, your images right now are of a size 32 by 1 by 28 by 28. You need to convert them to something that looks like this. So use a dot view function to essentially get it into like this weird size. I'll be real, this stuff doesn't really matter because it's AI engineering. And honestly, you can just use ChatGPT to get it into the size that you want to. That's essentially what I did here. And the second thing that you want to do is called the forward pass. So does anyone remember what a forward pass essentially does? It moves your input all the way to the output through the network, right? What you do is essentially your hidden layer 1 output will be your images multiplied by the weights layer. Remember, your input multiplied by the weights at the first layer. Then you put them through a ReLU function. That's the activation function. Now you get the output at hidden layer 1. You do this again by taking the output at hidden layer 1 and multiplying it by the second layer's weights. And essentially at the end of it, you'll get something that's called an output. This loss function is called cross entropy. That was the loss function that we discussed earlier with the y times log yi. And essentially you'll calculate your loss with this output layer and your labels. Your labels are the true prediction data. This output layer is your predicted data. This is the true data. The loss will essentially calculate how far your output data is from the true labels. And then you call dot backward. What will happen is all of the weights in the weight layer 1, weight layer 2 will essentially be updated to minimize the loss. And it'll move in like, it don't be minimized, my bad. Oh, sorry. Yeah. Don't be minimized. The gradients will be calculated for all this. So if you, for example, go to some weight in weight layer 1 and call dot grad over here, you'll get the gradient of that weight with respect to the loss. Now, the step that we looked at in the earlier example is the same. You take your weight layers, you subtract the learning rate, which is the amount you want to move in the direction of the minimum loss, and multiply it by the gradient. And you do this with weight layer 1 and weight layer 2. That means after one step, your weights have moved in the direction of lowest loss. And what you do is after this, you convert your gradients into 0, just as like housekeeping. To be honest, this doesn't really matter because every time you call it dot backwards, these gradients update, but this is just something you do. And we can now actually train our neural network. So I'll just wait for this to like train. Oh yeah. So can anyone guess? Okay. So good learning rate is something between 0.1 and 0.001. But honestly, it depends on the application that you're having. The issue is that a lot of stuff that I've described here, especially with like parameter optimization, is really high level. And I'm going to get like another workshop done on that, because this is basically how you create a neural network. But this is like part 1 of it. Part 2 is actually choosing like really good parameters, and that is like a completely different math background to it. But for now, it's a learning rate. Yeah, I'll just choose something like 0.05 for now. Or you know, 0.01 seems right. And I'll like train it. So again, to give you a wireless training, I'll like remind you of how it works. You have your weight layers initialized. You have 2 different weight layers with different weights in it. Each set of weights corresponds to 1 neuron. Your forward pass took your input, multiplied it by the weights in the first layer. Then you got layer 1's output. Those were put through an activation function called ReLU. That makes it non-linear. The output from layer 1 was put through layer 2. Then it was used to calculate a loss. The loss essentially gave you how far away your predicted output was from the true output. You called dot backward on it, and essentially after you called dot backward on it, what you got was all of the gradients with respect to the loss function. Then you updated it to basically reduce the weights in the direction of minimized loss. And then you did this for many different examples and for 10 epochs. As we can see, after the first epoch, the loss was 5. After the second epoch, the loss is somewhere around 3. Wow, it came down to like 0.89. Each time you run this, the weights are going to move in the correct direction even more. So there basically what is happening right now is here, these weights are slowly moving towards this direction. That's why the loss is decreasing after each epoch or after each runtime. So that what's happening right now is essentially this training process going on. We can like wait for it. And you might see that the loss might jump upwards sometimes. That's perfectly fine, because what we are doing is essentially you're picking different batches. As you can see in this stochastic gradient example, picking different batches will result in different loss functions for each different batch. That means this won't normally go down in this smooth of a path. It might zig here, zag here, and then it might go back and forth until it reaches here. So it's completely normal for your loss to like go up sometimes. Obviously, the way in which you know your loss function is doing something that's weird, if it's going really high up, then you know that something's going wrong. Okay, let's see if this should. It should.
So like with the loss increasing, do you think is that when it found local maxima, minima, and now it's going and trying to
With
find
the
a
loss
global?
increasing, what it could do is essentially, potentially, the loss for that particular batch was sort of different from the loss that was there for the earlier batch, or it went in different directions. And essentially, what happens when it goes into different directions, it counteracts. Like, for example, if the global minima is here, and your batch has a global minima that's somewhere around here, your function will go here. And then for the second batch, your global minima will be somewhere here. So you'll go back right here. And for the total batch, that loss might result in something going up. So this can happen like 0.1. The issue is that these epochs, theoretically, for this data set, which was around 10,000 to 60,000 images, should be around like 100. So this is like increasing a lot, because the thing is that I don't have enough epochs to basically run this for a long enough time. But if you run this for like something like 100 epochs, you should get a loss function that's really, really low. That's what theoretically should happen. Now, 10 is obviously not high enough of a number for this to like work correctly. 1 is a good enough loss function. So now we'll try some examples out. Okay, so this is a function that I've created. So remember, fashion MNIST is a data set of like fashion images. So what this essentially does is it takes an index to predict, it plots the image that's at that index, and it predicts your prediction for that particular image, and it basically plots that image as well. So a sample example is right here. The true label for this image was 8, and your predicted label was also 8. This is the same example. Let's do something else. Yeah, so as you can see, true label was 3, the predicted label was 3. You can play around with like different indices. True label was 4, predicted label was 4. As you can see, our neural network is doing pretty well. If I let this run for, let's say, I don't know, 90 more epochs, it would be really, really accurate. But obviously, we don't have time for that. So essentially, to recap, your neural network, the way you'll create neural networks, will probably be different, because you'll use something like pre-made PyTorch templates, and you'll sort of do something like that. Or you might use pre-made TensorFlow templates to create your neural networks. But the ground up understanding that I want you to have is you have different weights. You have different parameters for each different weight. What you do is essentially you put your input through the neural network. What I mean by putting it through the neural network is multiplying your input at each layer, getting your output, putting it through an activation function. You keep doing that until you reach your output layer. You'll have some output. You'll see how close your output is from your desired output for that particular example. You'll calculate that loss. You'll call loss.backwards on it to get the gradient of each weight in your neural network with respect to that loss function. And then you'll update it according to the method that I showed you. You'll keep doing this for like a set number of examples until your loss is really, really low. And then you'll basically use your neural network to predict for different things. For example, for this predicted label, I put in an input image and it did not know what it was supposed to correlate to. I just predicted it, and what it got was 4. And as we can see from the raw data right here, the true label was also 4. That means when you put in, for example, if I would have put in some random image of, let's say, a pair of shorts, and if the true label was 5 for that particular thing, I would have gotten the predicted label of 5. In effect, I've made a neural network in like an hour that can predict what piece of clothing it is based on these images. And that's pretty cool to think about. Like, it took an hour to do something that did something this cool. And essentially, if I had a faster laptop, it would have taken even less time. But what you can do for this is essentially, you can have neural networks that predict for text. ChatGPT is like a really good example of a neural network that does insanely complex things. You have DALI, you have different image creators that take an input of your text prompt and essentially map it to some random image that it had generated based on something that you had never seen before. What this does essentially tries to replicate that. There are some issues in this method, which are precisely, you may have overfitting. Your learning rate might not be a constant. So just like show you here, for this, imagine that you're getting close to this minimum. But imagine that the steps you're taking are like too large. So what happens is you keep on oscillating between this minimum. The reason why this happens is because our learning rate was a constant. But if it wasn't a constant, if it could sense how close it is to the minimum and then adjust it accordingly, that would make the neural network more accurate. it would keep on taking bigger steps when it was away from the minimum, and it'll take smaller steps when it's closer to the minimum. That way, you'd minimize the number of steps needed to get to something like this. That's a technique called Adam. Something else that you want to avoid is something called overfitting, which means that your neural network will basically learn how your data works perfectly. But when it's shown an example outside of your input or outside of your training data set, it'll like suffer. And that also tends to happen a lot. So these are some of the things that I might talk about in my next workshop. But does anyone have any questions about how a high-level neural network works?
What the middle ground would look like between the two? Would it still bounce, but be like closer? Like how would the
So you're saying that this is a really small step and this is a really large step. What would like a medium-sized step look like? It would come down here and it would like sort of bounce between this minimum. And that's what you want. That's what you want, essentially. You want to pick an appropriately sized learning step that will actually come down here and won't just like bounce from here to here, or it won't just like stay in this like small range. That's essentially what you want. Yeah.
I mean, you can just have like a smaller one and then just train for longer.
You can do that, again, computationally expensive. If you would have like a learning step that's larger and it gets like smaller, this closer here to this learning rate, you would have much less steps and the same amount of accuracy. So you could always do, like, as he said, you can have a really small step and train it for like a long time. That could theoretically converge to over here. But like, I mean, again, it depends on like how practical it is. If you can leave your computer running for that amount of time, or even if it theoretically can converge over here with that amount of step, then it is something that is possible. Those are things that I'm guessing if you guys are like solving things at like an undergrad level or an amateur level, you probably don't know. So potentially the only option here is to like experiment with different learning rates or look up learning rates for like similar problems online. That's like your only solution. Does anyone else have any questions? Yeah.
For the image side part, if you scroll down a little bit, what is the second image? The second like draft.
Yeah. So essentially, your input image is this. I have to like code this quickly. So what this is, it finds just to show how similar these are. It gets a predicted label and it cycles through the data set until it finds an image with your predicted label. So just to show that your predicted label is the same as like this. So essentially, your predicted label is for this image, but this is just to show that, like, I don't know, the first image that I got for like this label basically looks like this, to show that these images are similar in nature.
Okay, it's like for display purposes.
Yeah, it's just for display. This predicted label is for this image. It's not, it has nothing to do with this. Yeah. So, yeah.
And with your image, is it actually looking at each pixel and like doing the?
So you remember that the image is 28 by 28 pixels, right? So it looks at each pixel because your input was 784, if you remember. Each pixel is one of those 784. So it looks at each pixel and essentially calculates weights based on that. So just to like recap, does anyone understand how a high-level neural network works? Yeah, sort of, with like the parameter updating, the cycle, the how input moves from one end to the other end. Does anyone everyone get that? That's good, because that's like the under the hood part that you guys need to understand to create like really efficient neural networks. Like you can obviously like look up how to create a quick neural network in PyTorch and it'll be like at this step in like 2 seconds. But the thing is, once you want to optimize it, you need to know what it actually does to like actually get to like this step, right? I mean, you can keep playing around with ChatGPT with like different learning rates, but if you know that this essentially is going to happen with irrespective of what learning rate you choose, then you essentially know that your problem is ill-defined. So getting this under the hood understanding is really, really important. I hope with this, essentially, you guys can go home and like create your own neural networks without using any PyTorch templates. Maybe create something like this code example that I've given. Maybe create something like this on your own for like different data sets. You have something like MNIST, which does numbering data sets, and you have Urban 8K data set, which has basically different data rows for like sounds. So that's pretty cool to play around with. That's something I would try to get to do here, but it took like 5 gigabytes of data, so I don't think it was practical to like give this as an example. Yes?
So would this be considered some kind of like supervised learning because we have a defined output layer?
Yes. So supervised learning, for those who don't know, is a type of learning where essentially you train your neural network based on known labels. So as you can see, for all of the inputs that we trained it on, we knew what the answer was, and that's how we calculated the loss, right? For some machine learning problems, we just don't know that, and that's called unsupervised learning. But yeah, this is, as you're correct, this is supervised learning and in neural networks. Is anyone else? Yeah, go on.
So it would be, so if we were doing it unsupervised, we would have like a different kind of way of approaching the problem.
Yeah, so from my understanding, this is a really high dimensional problem. So what I mean by a high dimensional problem is essentially if you have higher number of input dimensions, as you can see, we have like 784 dimensions here. The higher number of dimensions that you have, the computationally harder it is to classify things into like different what do you call it, different classes. And essentially, as you can see here, you could have an unsupervised learning algorithm to classify these points or even these points potentially. Why? Because assuming that you don't know that these points are green and these points are blue, imagine that you just need to create an algorithm that sorts different points into two different classes. That's an unsupervised learning problem. You could do it for this. For problems of really high dimension, the big question is that firstly, they need to be separable in this way in some dimension in and itself. So your problem would need to look like this in some higher dimension for it to have a solution to begin with. We didn't want to tackle that here because that's pretty complex. But if you genuinely are curious about that, you can like talk to me after class and we can like figure that out. But yeah, does anyone else have any questions? Yeah.
So you're saying unsupervised learning only works when the problem can be abstracted to a linear problem at the end of the day?
Not a linear problem, but a separable problem, if I have to be correct. Because if you have like, let's say if you have three different sets of points, then you can essentially have some, I don't remember exactly how it works, but essentially if you have three different sets of points that look like they belong in different classes, potentially your solution might not be linear. Though as far as I remember, it needs to satisfy some criteria in some higher dimension for it to be solvable. Now, for this potential example, imagine that you just project these points up in 3D and you keep these points down. You can draw a line that bisects them in 3D. Imagine these points come up and you draw a line, then you have basically anything above this line is blue, anything below this line is green. So that's a potential example of how you can solve things. I'm not exactly clear whether this problem needs to be linear in some higher dimension for it to be solvable. But if I remember correctly, it needs to have some, it needs to meet some sort of criteria in order for it to be solvable. That's why unsupervised learning is sort of harder than supervised learning. But yeah, that's if that answers your question. Any other questions? Is everyone sort of comfortable knowing how neural networks work? I know I have to like rush through a lot of this because of technical difficulties, but does everyone have like a good feel of how it works? Yeah.
Can you just like explain the dot backward function?
Yes.